The good thing about my talk, I hope, is there are no equations. It's a fairly kind of informal talk, and really I'm looking for input from you guys as well. Whether you tell me this is a good way to do some research or maybe not. So, no need to talk about that. So what are chopped vortices? Unfortunately, chopped vortices are not very well known in the fluid mechanics area. Mostly known in aeronautics. Typically, if you have a flow around a high Reynolds number flow around a bluff body like this is the expectation. You get a large chain of separated vortices. You have an unsteady wake, a lot of drag, very low lift, and so forth. However, if you're clever enough and you introduce something like a cavity where you kind of entrain this flow into the cavity and make sure it stays stabilized, then you get what we call the chopped vortex. So the vortices are trapped inside that cavity. This is what chopped vortices are. A result of that, there will be, unsteadiness will be reduced, less drag, and more lift. So it's very, of course, very good idea. Now, very quickly, historically, it's a strange the way it develops because it kind of anecdotal evidence or hypothesizing about this. Many years ago, someone with a glider at very low speeds who said that it's Caspar, who said that the lift to drag ratio is very high at very low speeds, which he thought was due to this large scale chopped vortex on the top of the wing. Now, some research was made in Russia. This is called the IKIP flight, the IKIP aircraft, and they claim that it has these central bodies with cavities with central bodies which are able to chop the vortices and increase the aircraft performance. This is only, of course, a small scale model. Right. Luckily, in the last few years, there has been some research to try to kind of ignite this research area again, and there are some recent work. Part of my PhD work was actually on chopped vortices using CFD, and now I'm at the university. I would like to look at it, but in terms of kind of looking areas of ground vehicle rather than aeronautics. But just very quickly, very recent results by Tati and authors in the University of Southampton who did both numerical work and experimental work on, as you can see, a wing with a cavity. These red dots show the position of pressure tappings, and they got some interesting, encouraging results. Other research is cited as well. So there is some kind of encouraging results to start from and try to think about ground vehicles. Very quickly, what was observed is that to be able to have the benefits of chopped vortex, it has to be stabilized all the time. So there has to be a mechanism of flow control, typically suction or blowing. It means you are spending energy, and if it's not stable, you get to the image I started with a lot of separated flow, which makes it useless. Now, very important when you talk about vortex stabilization, we're talking about with respect to large-scale vortex shedding. We all, we all know. Now, one reason we want to extend this idea to ground vehicles, because although there was funding for some research into wings and fuselage aircraft, because the goal was towards 2050. It's very difficult to get some funding. So I hope some of you get excited by this idea to apply it to ground vehicles. Well, why is ground vehicles? Many reasons, really. They're good examples of bluff body shapes, high Reynolds number flows, and therefore there will be a lot of separation around the vehicle. When there is separation, of course, we want to trap those vortices and use it to improve the performance of road vehicles. As I said, very difficult to do it in aerospace industry because it takes a lot of time. So the hope is, can we actually make it cheaper or quicker when we think in terms of ground vehicles? And the good thing, of course, there is a lot of supporting research that has been done we can start from and learn from and see if it is applicable to ground vehicles. Right, I'm going to start with road cars. Of course, there are a lot of ground vehicles, but I'm just considering 4 in this talk. I know this is a very old image, but part of it still probably true. And basically, as old friends have been talking, you get a large wake behind the vehicle with a low pressure area, and this increases the base drag, which is a big problem for road vehicles. Now, people claim different things, but I'm just putting up to 50% of the total drag around the car is due to that. Now, this table, you can argue with me whether it's true or not. Again, various sources say different things, but at least there is 30% at the rear end, 15% on the wheels, and underbody is 30%. So there are definitely areas to improve the performance of road cars, hopefully using trapped vortices. And really simply, from an aerodynamic point of view, what we want is maybe decrease the stagnation pressure on the front of the car or increase the base pressure, or both. Can we actually do this? And of course, from an aerodynamic point of view, one central aim is to really decrease the size of that wake behind the vehicle. If we can do that, we can decrease the pressure drag and therefore the overall drag. Now, one thing that, of course, the trapped vortex was initially on aircraft, and it's on the top of the wing. We can't do that with road cars. So having a trapped vortex on the top of ground vehicle does not work. It actually gives you more lift, which no one wants. However, if we think in terms of the flow underneath the body, there is hopefully some potential to do that, because that will, if you create a low pressure area underneath the body using a trapped vortex, then your net downforce will increase. That will improve the road adhesion for your vehicle. Also, if you entrained a lot of flow underneath the body, the hope is less of it will be affecting the wake, and less of it will be entrained, and therefore you reduce the size of the wake. Don't worry about that one. Race cars, pretty pictures. But now race cars are different to road cars, because you can argue is really what you want is to win the race. Not to say reducing drag is not important, but really one very important thing for race cars is to have a really good cornering speeds and a lot of downforce on your car to win the race. That's why that's what the main aim is. So so the central aim for race cars is really the downforce, but also the drag. Okay, usually we have inverted wings with race cars, and in terms of creating the downforce, they contribute about 50%. And one suggestion could be that for the inverted wings, which are usually at the back and at the front, we can put a leading edge flap. This will create a very strong vortex underneath the wing, so therefore a very low pressure area, and you get more downforce. That's very good for the whole vehicle. Now, as I said, the main problem with trapped vortices is that they have to be stabilized at all time. So that's not enough. What you need to do is probably use some kind of suction somewhere to actually make sure the vortex is always stabilized to have this continued increased force. Now, of course, compared to aircraft, road vehicles, they have to, negotiate with the ground. Now, there was a couple of probably 3 studies, not many, but very encouraging one back in 2003 by Garcia and Katz. They used vortex generators and a moving ground to look into this idea. And encouraging results, they found that the trapped vortices which were created by vortex generators underneath the car, they were able to increase the downforce on that racing car. And of course they did not, this was an experimental work, they didn't have the whole car, but they simulated the lower part of it. So we have some encouraging results, and also some agreements were made later by other experimental results as well. Now, if we look at the underbody diffuser, typically we have a lot of flow separation here, and that's what we want to make use of. So instead of flow being separated underneath the car, can we actually trap that vortex, create a low pressure area, and improve the downforce for the car? So both you have the wings, the inverted wings, as well as the underbody are potential areas to do this. Now, if you want to create stronger vortices, one suggestion could be maybe to have flaps here again to create stronger vortices, which then you kind of trap in that area. NASCARs, this is, I'm not sure where I got this picture from, but well, just to illustrate the point that, you know, the underbody flow is very important, but it's very much separated and steady, and there is a lot of flow we can deal with and trap underneath the car as well. So if we can do that, that will again create a lot of downforce on the car. So you can see quite simple ideas, but we're trying to apply them to these ground vehicles. Commercial tractor trailers, typically, if you want to improve the performance, for example, you look at the front of the vehicle, you see here, for example, kind of streamlined. Also the gap between the trailer and the front has been reduced. And basically what you want with aerodynamics is to decrease the number of separated regions. If you can do that, the overall pressure drag will reduce. This is just typical picture of where are the high drag areas. So typically, as we expect, the front, again, the underneath of the vehicle, that gap is quite important, and also at the back of the vehicle, as you would expect. So all those areas are real, practical, potential areas to apply trapped vortices. Now, there was one study, very encouraging one, which looked into trapped vortices, and basically, this is very specific application where at the forward face of the trailer, there were these vortex trap devices, and as the flow passes away, you create this, you guys can see this trapped vortices from one section to the next. Now, as you think about it, this will create a low pressure area on the side of the trailer, not the other side of the face, and the overall, you will decrease the drag, as you'd expect, just pressure difference. Don't worry about that. Another idea that was tried was not necessarily trapped vortices, but this idea of vortex strake devices, which were put towards the end of the vehicle. And the idea is very simple, really. Normally, you have a very large wake with a lot of smaller, large-scale vortices. What you want is try to kind of break up that structure and make the size of the wake as small as possible. Potentially, these kind of streaks here, strakes, seem to be helping. So that's another proven idea that relies on the use of these devices. Now, with these combined, there was 8% reduction in the total drag. 8% in the fuel saving, and total percent in drag reduction. So they're very simple, valuable, and they work. You know, they're very simple ideas, but they work. And the hope is, can we do more to increase that number from 20% to something maybe more? Finally, high-speed trains. The two things I would like to mention are high-speed trains in crosswinds, and high-speed trains in terms of the effects of slipstreams. So very quickly, if you have a high-speed train here and there is a crosswind coming from left to right, you will create a side force, as you would expect, and then the flow goes up around the body and also underneath. You get a low pressure on the other side, high pressure this side, and then you get a side force. You also have to deal with the lift force, unfortunately, and also there will be a turning moment. Now, the thing about high-speed trains, they're very lightweight and they're very kind of streamlined, which make them very susceptible to overturning. And believe it or not, a lot of accidents have happened in the past. Now, the nice thing is that they also depend on the Reynolds number, critical, subcritical, and so forth. And the idea is, again, is very This the same thing really. How do we improve the stability of high-speed trains in crosswinds if I can use this idea of chopped vortices? And very simply, what you want is you want low pressure this side and high pressure this side. And the idea here is, well, can we use it underneath the vehicle? I don't know, I'm not sure, but at least physically it should work. Slipstreams, I'm not sure how you have the experience if you are on the platform and the train passes and you get all the wake from the train. That's simply what the slipstreams are. Many people have been hit by that, things flowing around. So that's another idea where we can reduce the effect of that using the chopped vortices. Main challenges, sorry, I'm running out of time. Now, of course, we're dealing with unsteady separated flows. We have to have some kind of flow control, passive or active, to stabilize the flow at all time. If not, it's not really very useful. Can we combine this chopped vortex idea with other existing methods on ground vehicles? Is it complex? Is it really feasible? We can discuss, not a problem. So conclusions. I think there is good evidence to suggest that ground vehicles really provide a nice area of research to the potential of chopped vortices in a number of ways: reducing drag, increased downforce, decreasing unsteadiness, crosswind stability, and so forth. Definitely, we cannot implement it on the top surface. We have to think about the ground effects, clearly. And the basic issue that will always be there is how do we keep this chopped vortex stabilized all the time so you don't have vortex or massive vortex shedding. But this is just some work I'm looking at the moment in terms of joint solvers and system identification. And finally, the references relevant to this talk. Thank you very much.